Hey class, so glad to have you on again. I'm going to be doing section 2.2 now, which is about conditional statements. And I have the notes I'm about to share, but remember the notes are also on Canvas too. All right, so let's go ahead and start sharing screen here. There we go. So here we go about conditional statements. So what we care about here is that we're going to be learning about how to express things in if then. So a conditional just means that we're saying if something, if blah, 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 then something else, like that. And we use it all the time in normal everyday language. So it's really good to be able to talk about it in terms of logic. And most propositions or theorems that we're going to try to prove in this class, or things about algorithms too, are written in if thens. And if you've ever used Excel or any not just Excel, but any computer programming language, they use ifs all the time. So it's good to know for us to how to express it and work with it. So let's jump right in. So when we're talking about a conditional, again, we say P and Q here are statements, like just something we're talking about, depends on what we're working on the problem. But the way we say it is that if P, then Q. We might also say P implies Q, but we mainly are going to be using this P implies Q, so like that. So if P, then Q. So we read it that way. It's just a single arrow like that. In a lot of other math books, they use different arrows, so you might see it in your other future math journeys like that with the equal sign and then like a so different type of arrow. But we're not going to be really using that. So in our class, we're just going to be using this. So P implies Q. Okay. P is the hypothesis and Q is the conclusion. Now, what's weird to start right off the bat is that we're going to be talking about how to verify if something is true, if a conditional is true. But what's weird is that there's this weird case where if the hypothesis, if this is false, so if P is false in your conditional, then the entire then the conditional statement as a whole is true. Is what's called vacuously true. So let's talk about that and vacuously true. You don't really hear the true by default. It's more vacuously true. So for instance, when we have like this conditional, for instance, this would be like our P here, and this would be like our Q. So we have P implying Q. The if then is wrapped up in the arrow here. So P implies, I can't draw an arrow. P implies Q there. So if 0 equals 1, then 1 equals 2. Now this is false by default. So P is false. You can't, that's not true, but because P is false, remember P is the hypothesis, it's the beginning of the conditional. Because P is false, the whole conditional is true, it's vacuously true. Statement is vacuously true. Now, vacuously true just means that it can't be disproven. It doesn't mean it has any value to us that we care that it's vacuously true. Some other ones, it's easier to come up with. So something like, if birds bark, then I'll win the lotto. Birds don't bark, they chirp. But because this part here, the hypothesis P here is false, then there's no way that we could ever get to here. But even though we can never get to here because the conclusion is, the hypothesis is false, the entire statement is true. So this is a vacuously true statement. That. Another thing you can think about is that if something like this, if it rains unicorns, then I'll get a PhD. Now, the whole statement is true. It's vacuously true. This is never going to happen if it rains unicorns. But because the hypothesis here is false, the entire statement is vacuously true. And again, I'm talking about me getting a PhD. I don't ever want to get one, but I'm sure actually some of you will be getting one. But the hypothesis is false, so it doesn't matter about the conclusion. But overall, the statement as a whole is vacuously true. Just a quick thing, someone asked about in the last class video that the order of operations. So we do the conditional last. So we do these first. Okay. So do the not and then the ors and ands first. Okay. And we do the not first. We negate things first. Okay. So let's jump into, we talked about truth tables last time. So let's jump into how to prove that we want to make a truth table for this statement. P or not Q implies not P. Okay, and let's find out when overall is this true. Okay, so when is this overall going to be true? Well, it's going to be overall true, by the way. It's going to be vacuously true when the first part is false, because we just talked about that. If the hypothesis is false, then the whole statement will be true. But let's talk about it. So let's go ahead and write out the truth table here. So draw out your truth table. There are only two statement variables here, P and Q. So I'll just call P and Q. Let me erase this one. P, Q. And remember, these are the automatic ones. So we can just say, okay, true, 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 false, false, true, and false, false. Okay. So remember, we fill that part out automatically anytime we do a truth table. Then we look at, and what else do we have in the conditional here? Well, we have not Q. So I'm going to need not Q. Actually, I need not P as well, don't I? So let me write the not P. Yeah, that's fine. Not P and not Q. So I need those as well. And remember, this just flips. So not P is going to be the opposite of whatever P was. So false, false, true, true. Not Q is going to be false, true, false, true. Okay, hope I did that right. Now let's start doing the other things, the building blocks. So we need P or not Q. So P or not Q. Oh, sorry. Like that. Okay. And P or not Q. So let's take a look. So this is going to be true as long if I just have at least one of them or both of them. Just one of them need to be true. So let me look. On this row, is P true? Yes. So that means this or is true. Same thing on this row. I have a P is true, so that's true. Now this third row, P is false, but the question is, do I have not Q? And I do not have not Q. So not Q is false and P is false. So that means this or statement is false. And then finally, P or not Q down here. P is false, but I do have not Q. So that means this is true. Because remember, an or statement is true as long as we have one of the ors, either parts of the or. All right. So then we can answer a question. What about the conditional overall? P or not Q implies, sorry, can't draw arrows today, implies not P. Well, so we want, we're going to have a true statement. So conditionals are going to be true. When we have true implying true, and also false implying true, and also false implying false, like that. Basically, conditionals are only false, so only false when false implies true. Sorry, true implies false. When we have a true hypothesis, but the conclusion didn't happen. Like that. Okay, so let's look on here. This right here is the hypothesis. So we want to look, it's going to be true when the hypothesis here is true. Or actually, sorry, to make it easy, we can look right away for when is the hypothesis false. So false hypothesis. So false hypothesis is only right here. So this is going to automatically be true. Because I had a false hypothesis, in any case of the false hypothesis, it's going to be true there. Okay? Now let's look. The only other time I'm going to have a true statement is when I have true leading to true. So I want truth in the hypothesis and true in the conclusion. So I have true in the hypothesis here, here, and here. And let's talk about the conclusion, because the conclusion is here. So let's see. Hypothesis is true. Does it lead to true? No. In fact, I have true leading to false. Again, true hypothesis leading to a false conclusion. That's right here when I have a true leading to a false. So that means it's false right here. Okay. And let's go down here for the second one. I have true also leading to false. So that's going to be a false conditional as well. And then let's check down here. I have true leading to true, like that. And so that's true right here. So we just found the truth table. We found out when this conditional is true. It's only going to be true in these two cases right here. So overall, this is true only when we have right here and right here. When P is false and Q is true, or when they're both false, like that. Okay. And you can go back in the video and make sure you capture all that, okay? Yeah, so same thing. Okay, false, false, true, true. So let's talk about logical equivalences, equivalencies involving the conditional here. So remember what we talked about. The way you show something logical is logically equivalent is you construct their truth table, and they have to have the exact same, their rows have to be exactly the same, meaning that when one is true, the other is true. And so when when this guy here is true, this guy must also be true, and vice versa. When this guy is false, this one also must be false. Okay. Now this one is quite long again because we have three of these statement variables, P, Q, and R. So let's just say that, and then we're going to do this as well. So go ahead and just on your own, check out the answer that I have built here for you, okay? Notice that there's 8 here. This is the automatic stuff because P, Q, and R are the 3 things. So we need 8 of them, okay? But this idea is the same. You build up all the different parts, the P or Q part, and then you do that. And then you also build up this and this, which are going right here. And then you have the kind of like the conditional. So this is the first thing that we're trying to show is logically equivalent to this one, to number 2. Okay. And that's what goes on right here. And let's check. So after we did step by step and we filled out this table, if they were logically equivalent, then we'd have to have exactly the same rows. So this column would have to look exactly like this column right here. And let's check. True, true, yep. Okay, that's good. False, false, yep. True, true, false, false, true, true, false, false, true, 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 true. Okay, so they always have the same truth values, so then we can say that they are logically equivalent. And that's cool. So that means if we ever have to work on a problem that looks like this, instead we can just work on the simpler one like that. P or Q implies R, which is nice. And I'll let you go back in the video and pause the video and copy that truth table down, okay? But that's kind of the idea. So this is super important where we're going on right here. Super important. I think I might even make a quiz on Canvas to make sure that you get this idea. A lot of times working with if then is actually kind of hard on problems that we want to do. So it's actually better to use the equivalent statement of or. So again, yeah, I wrote super important. If then can be written as an or statement. All right. So the big idea, and like you can put this in a big box so that you kind of remember what's really important, and is that P implies Q. Okay. If P then Q is logically equivalent to this, not P or Q. And it's kind of hard to think about. I mean, you know, language is kind of rough to work on, but if you have something like this, like say, if I work, then I'll make money. So say that's my statement here. So this is P and this is Q. Okay. So that's the first side. That's the conditional. What would this side look like if we're saying that in English? It would say I don't work. So this right side would say either I don't work or I make money. And it's kind of subtle, but that it turns out that they're equivalent. So saying this in English, either I don't work or I make money, is logically equivalent to say if I work, then I'll make money. Okay. Yeah. So let's prove that with the truth table here. So how do we do that? Well, we have we have just two things here, P and Q. So we build a truth table. Here's P. Why do I do that? Okay. Here's P. Here's Q. These are the automatics. So true, 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 false, false, true, false, false. Okay. And then you have up here, let's see, what do we have our building blocks? We have not P, so we need not P. And then we need not P or Q. Okay. And then we need one more, which is this last one, P implies Q. So let me separate that here. And then P implies Q. All right, so not P. Not P is just the opposite of P, so false, false, true, true. Okay, so that's cool. Now here we have not P or Q. How are we gonna do that? Well, this is true when we have one of them. So do I have Q here? Yes, I have Q, so that's true. So that's good. I don't have Q here, and I don't have not P, so this is gonna be false. And then do I have Q here? Yes, I do, true. And then down here, I don't have Q, but I do have not P, so that's true. So this right here is the column for, let me erase that. This is the column for the first thing that we're trying to show, is it equivalent. So true, false, true, true. So if we do it right, then this one also better be exactly true, false, true, true. Well, what did I talk about? This is only false when I have a false, sorry, it's only false when I have the hypothesis. So when P is true, but I do not have Q. So let's see, when do I have P? Only here and here. And when do I not have Q? Right here. So on this row, I have a true hypothesis right here. This is the hypothesis, but I have a false conclusion that didn't happen. So that's going to be false. Let's check. Everywhere else is going to be true because a conditional statement is true everywhere else. So conditional statement here, true leading to true, that's good. So that's true. So a true hypothesis led to a true conclusion. What about down here? Well, I have a false hypothesis leading to a true conclusion, but again, that's vacuously true. Anytime your hypothesis is false, it doesn't matter what the conclusion is, the overall conditional statement is true. And same thing down here. I have a false hypothesis leading to a false conclusion. Logically, that's still a true statement. It's just vacuously true. But check it out. So on these two columns, I have exactly the same check, 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 check. So that proves that not P or Q is logically equivalent to P implies Q. And I can't tell you how important that is. So make sure that you understand that. I'm gonna put stars here. And I might make a quiz about it too, because it's so important. We're gonna be using it literally for the entire semester. When we're gonna be trying to prove theorems that are P implies Q, a lot of times we're gonna actually just try to prove this, try to prove not P or Q, and vice versa. Okay, so we're gonna be moving back and forth. Okay. So how do we negate a conditional statement? We are going to use the or form to help me do that. And how do we do that? So if you want to say what is the negation of a conditional, so if P then Q, how do you say, well, what's the negation of that? Well, the negation of if P then Q is logically equivalent to P and not Q. And that's here in this box right here for you. So the negation of a conditional is logically equivalent to just this, P and not Q. Why is that? Well, let's see. Just use De Morgan's law. The negation of P implies Q, rewrite P implies Q as, that's logically equivalent to using De Morgan's law as just rewrite P implies Q as not P or Q. Okay, that's the big idea that we just had in the last slide. But then what does De Morgan's law say to do? Well, if you have, so this is definition of the conditional. Well, what does Morgan's law, De Morgan's law say? It says distribute the negations. So not P is P, and put it there and put it there. It's going to be not Q. But then remember what it does. It takes this not or and it flips it to that. So ta-da. That's it. And that's what that box is. So that's by De Morgan's law. You, of course, could also prove it using a truth table too, the old-fashioned way. You could just take this truth table right here and prove them as well. Okay, let's get practice here. Right, let's write negations for each of these. Let's get practice in English. We've been doing kind of abstract with the variables here. So if my car is in the shop, in the repair shop, so that's P here, then I cannot get to class. So again, we want to write the negation of this. So the negation of that, well, up here it says the negation of a conditional is the first thing, the hypothesis, and not the conclusion. So I'm just going to write the hypothesis. My car is in the repair shop. And I need to negate this, and I can get to class. It's a really sloppy can. So, and I can get to class. Okay. So again, it flips it there because it has to negate the last one. Okay. And same deal here. If I want to negate this, again, this is P. This is not Q. Sorry, this is Q. And so I know that the negation of that's going to be, P and not Q. The negation is going to be that. So I just write it out. So Sarah lives in Athens, and she does not live in Greece, which is impossible, right? Well, assuming that we're talking about Athens, Greece, but yeah, so that's negation. Okay. All right, cool. So let's talk about the last few things we're gonna talk about is contrapositive, inverse, and all that stuff. Okay. So contrapositive you might have seen in geometry in high school. Okay. And the contrapositive says if you have a conditional of P implies Q, its contrapositive is you reverse order. So the conclusion becomes a hypothesis and vice versa. And you negate both P and Q. So reverse order of P and Q and negate both P and Q. Okay. A really easy example is like if I say, let's do the one I said where I work. If I work, then I'll make money. And we're talking about not in like a, communist regime here, okay, in capitalism, with labor laws. If I work, then I'll make money, okay. So the contrapositive version of that is, so this is the original. The contrapositive would say, if I don't make money, then I don't work. Like that. Okay, I flipped it, so the make money became the hypothesis over here, but I negated it. So if I don't make money, and then the work became the conclusion over here, but I negated it. Okay. So again, P implies Q. The contrapositive it means you flip it, you reverse the order, and you negate both. Okay. If not Q, then not P. So what's really cool, this is another super important thing. It's in a box. Okay, super important. Is that a conditional statement is logically equivalent to its contrapositive. What does that mean in symbols? What that means is that P implies Q is logically equivalent to not Q implies not P. Okay. This is so important because a lot of times when we're going to try to prove something like conditional, P implies Q, a lot of times it's like almost impossible to prove the left, to prove this. Like it's almost impossible to prove the conditional one way, but we can be clever and we can say, well, let me prove the contrapositive. So if you can prove this on the right side, then you're good to go. I'm actually going to kind of run out of time here on this because the video is already long, but you would just use the truth table here and you would go from there. I think I might post a picture of what this truth table looks like or a link to it, okay? But you would show it using the truth table. By laws, I meant you can also do by De Morgan's law. Actually, you can do it De Morgan's law right here. So let's work on the left side. So the left side is P implies Q. Remember, that's logically equivalent to not P or Q. Okay. So what about this one? Well, this is going to be logically equivalent to, so let's work on that. So not Q implies not P. Using that or form, the or form of that would say not Q or not P. This is the or form. Like that. But guess what? Not Q is Q and or not P. Like that. Well, ta-da, that is the same thing. So check mark, not P or Q. The or doesn't matter, by the way. Or is commutative, so it doesn't matter the order I have. I mean, you could say that's the same thing as not P or Q, which is right here. So they're the same thing. Okay, so that's faster than a truth table on that one. All right. So really quickly, let's write these in contrapositive form. So again, this part is the P. This part is the Q. So the contrapositive would say if Howard can't swim to the island, then Howard can't swim across the lake. Okay. Easy peasy. Same thing here. Today is Easter. Tomorrow is Monday. So the contrapositive would be if tomorrow is not Monday, Monday, then tomorrow, today is not Easter. And that's true because Easter always falls on a Monday here in America. Okay, cool. Not P implies not Q. So last little bit here is the converse and the inverse. Okay, you've probably heard that from high school geometry as well. So again, if we have a if P then Q, the converse is just reversing. So you reverse the hypothesis and conclusion. So it becomes if Q then P. This is negating, negating P and Q for the inverse, okay? And you can have it here as well. The converse of P implies Q is Q implies P, and vice versa. For P implies Q is not P implies not Q. Okay, let's get practice real quick. So the same guy, Howard, P, Q, the inverse would be, so all you do, you don't flip anything, you just negate it. So if Howard can't swim across the lake, then Howard can't swim to the island. Okay, and same deal here. This is P, this is Q. Oh, sorry, that was just the inverse. So what would the converse be? Well, I'm gonna run out of room here. The converse would be you do Q first. So if Howard, if H can swim to the island, then H can swim across the lake. No negating here when you do converse. Okay, and I'll let you do this for Easter and Monday as well. Yeah, you can do that. You can try that. Okay. So it turns out a really important thing is that converses and inverses are not logically equivalent to the original statement. So in symbols, that means let's do the converse one. In symbols, we'd say P implies Q is not logically equivalent to Q implies P. And for the inverse, what that looks like symbolically is P implies Q is not logically equivalent to not P implies not Q, like that. Okay, and I mean, we kind of know that because for instance, like on this one up here, if today is Easter, then tomorrow is Monday. Let's look at the inverse. The inverse here says, if today is not Easter, then tomorrow is not Monday. That's not true. You know what I mean? Like there's lots of days that are not Easter. So for instance, today, I'm recording this on September 3. Today is not Easter, but tomorrow is not Monday. Today it's Thursday, I'm recording it, and tomorrow's Friday. Okay, so today is a false, today shows you that this statement here is not true overall. And the same thing with the converse. The converse would say if tomorrow is Monday, then today is Easter. Not necessarily, because all the Sundays that are not Easter Sunday, that's still true. If tomorrow is Monday, then today is Easter. So anyways, so it's really important to know that the converse and inverses aren't logically equivalent to the original conditional statement. And this is important too. It turns out that the converse and inverse are logically equivalent. So what does that look like symbolically? P implies, Q implies P is logically equivalent to not P implies not Q. And again, you would just show this with De Morgan's laws or with truth table. They're pretty easy to do. Okay. You're going to hear the word only if a little bit in your book. it's not that important to me. What's really important is the word biconditional. Okay, biconditional is super important, and what it says is that P if and only if Q. We write that with the double arrow here. You also might see me write if. This stands for if and only if. Okay. So this is a lot harder to do. It only happens when both P and Q have the same truth values all the time. Okay, so it's harder, it's more restrictive than just the regular P implies Q. Okay, because the regular P implies Q, it was only false when we had a true hypothesis leading to a false conclusion, but the biconditional has to be true both ways. So what that means for us is that to be true, let me say for P implies, for P if and only if Q to be true, we must have both P implies Q being true and Q implying P being true. So it's a lot more restrictive. We need both of them to happen. Hopefully I wrote this down. Okay, I did not. Let me, this video is already long. I think I can do a quick here. Okay, good. So the truth table for the biconditional, P, Q, and again, the biconditional reads like this: P if and only if Q. These are the automatics. Again, we can always write this: true leading to false, false leading to true, and false leading to false. And then we just have the thing we care about: P if and only if Q. Okay, and it's only true when we have both of them matching exactly the same. So only true when P and Q have the same truth value. Okay, so that's that. Okay, this is just a summary for you. You can check this out later. Okay, again, we do negations first, and then we move on to the ors and ands, and then we do the ifs and thens, the conditionals. Okay. Let's get this going here. So just to get you practice, this computer program is correct. So let's call that P. And what we're going to do here is we're going to say conjunction of two if-then statements. So basically, I want to say right now it's written as P implies if and only if Q. What I want to write is a conjunction. I want to say P implies Q and Q implies P. So let's try that. If and only if it produces correct answers. Okay, so you would just say, okay, computer program is correct if then it produces correct answers. Dot, 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 you get the idea. Okay, but then I write it the other way as well. And I'll say, and if it produces correct answers, dot, 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 then it is correct. And the computer program is correct. Okay, all I did was this. I just did that in words though. Okay. All right, come to the end here. You'll hear me say these phrases a couple times. It's not super important, but just to let you know, You'll hear me say sufficient and necessary, especially you'll hear it in other classes too, and in the wider math and computer science field here, they use sufficient and necessary. So sufficient is a shorthand to say if R then S. So it's a sufficient condition. Work is a sufficient condition to make money. So that's what I would say. So let me try that. Work is a sufficient condition to make money. Condition to make money. Okay. Necessary is different. It's saying that if not R, then not S. So how would that work? So if not R, then not S. It would be like if I'm not, so let me try that one. So this was this one. So necessary, it doesn't mean it's sufficient. And so it just means that it's necessary. So if I don't, all right, let's do this one though with R and S here. Should that be easier? So if R then S, so that was if I work, I go to money. So that would say if I don't work, then I don't make money. Now these aren't the same. There's lots of people who make money so without doing work. Social media stars. People on YouTube. No, just kidding. They work a little bit. But people who inherit money, there's lots of people who don't work, but yet they do make money. So you can see that this is not the same as this. So they're not logically equivalent. So sufficient and necessary aren't the same. They're different. Okay, so for instance, this says Pia's birth on U.S. soil is a sufficient condition for her to be a U.S. citizen. Well, again, going up here, sufficient condition means if R, then S. So this would be R, and then this would be S, U.S. citizen. So the way we write that in if statement is if Pia was born on U.S. soil, then she is a U.S. citizen. And so you see, sometimes we have to change the language a little bit to make it match the grammar of English, but it's all good. Okay. And last little bit here, use the contrapositive to rewrite the following statement in 2 ways, okay? George attaining age 35 is a necessary condition for his being president of the United States. Well, again, necessary says if not R, then not S. So this is R, this is S. So let's write that using the if then. So that would say if George does not attain 35, which means he's 34 or younger, then he can't be US president. Okay. So that's the equivalent way of saying that. So this is the conditional one. But I asked you to say I asked to also do the contrapositive. So what would the contrapositive be? The contrapositive would say, okay, again, so this is can't be U.S. president. So contrapositive means you flip it. So so this was R implies S. So the original was R implies S. The contrapositive would be not S implies not R. So let's write that. So it'd say, if George can be president, U.S. president, then George has attained 35 years of age, age 35. Which is true. So again, this statement here, number one, is logically equivalent to number two. They're the same thing, just written in differently. Okay, so let me get back to Zoom here. So that's it for that one. The main thing that I can't stress enough is to go here in the boxes, okay? Especially the ones I said are super important. We have a lot of definitions here, and it's all kind of abstract right now, but it'll get easier as we work on. But we've learned about contrapositive, converse, inverse, sufficient, necessary. But the main thing I can't say is, you know, this one, so this is really important, the negation of a conditional statement. And the way we got there was by talking about this one. So this is very, very important. Okay. Okay. So anyways, have fun with that. And otherwise, I'll see you back in class. Thanks.